Okay, hi class. So this is last section in chapter 4, customized doses. Our learning objectives are to calculate drug doses using the ratios and proportion and dimensional analysis method, calculate doses based on weight and body surface area, calculate a pediatric dose using the patient's weight or age and the appropriate adult dose. So customized doses. Most manufacturers offer dose ranges as prescribing guidelines. In some cases, the suggested dose may be based on the patient's weight or the patient's weight and height. In these cases, it's necessary to calculate patient-specific doses. So like we mentioned earlier, manufacturers have just a range of doses. It's not necessarily patient-specific. So whenever they were doing their research and, they had their case studies, and they realized that, okay, the majority of the patients, what do you say? They had a range. So less than 25 milligrams, nothing was happening to the patient's body. More than 100 milligrams, the patient's body wasn't acting like it should. Okay, so it was overdosing and underdosing. So no, they knew that the range would be, the patient would have to get more than 25 and less than 100. So they end up with a 50 milligram tablet and they put that into the market. So that medication is only available in 50 milligrams, basically. But with customized doses, sometimes the physician says that, the patient needs a little bit more than 50 milligrams or needs a little less than 50 milligrams to get the desired effect of this patient. So that's where these customized doses come, when it's not available for us to purchase by a manufacturer, but we're able to manipulate that medication to fit the needs of the patient. Okay? So calculating doses based on weight, the patient's weight may be especially important when calculating a customized dose of a medication. Medications that have a small margin of safety should have a customized dose. More commonly, pediatric, ages birth to 18 years, and older adults, ages 65 and above, often need customized doses because their weight differs from that of a typical adult patient the medications are designed for. Okay, so like we stated earlier in the previous example, these case studies are usually the average adult. Okay, so that means basically patients older than 19 and older and lower than 65 and under. Okay, so that's why it's saying that for pediatric and elderly people's, the dosage must be based on their weight and even their height. Okay. Also, the body systems of pediatric and older adults patients do not metabolize or eliminate the medication as an adult body might. So remember, as a pediatric, our metabolized system is not at its fullest. So in a child, we notice that our metabolism is faster, correct? So as we age, our metabolism becomes stable, or in some cases, it gets lower. And that's when we get to adulthood and elderly, where the metabolism is so slow that the medication might be in their system longer. and we don't want the medication to stay that longer, so that's why we reduce the dosage amount. And the same thing for pediatrics. Since their metabolism is so fast, that medication might be in and out of the system right away. Okay, so that's when the dosage has to differ. So in these cases, manufacturers will often offer prescribing guidelines for medications based upon that therapeutic amount or range per unit of body weight. So remember, they have done all this information in their case studies, and they have to have this available for those specific situations. The most common unit used is milligrams of medication per kilogram of body weight, or mg per kg. So for example, a patient weighs 60 kilograms and she is to receive a medication of 15 milligrams per kilogram. If the medication is available in 300 milligram capsules, how many capsules will be dispensed for one dose? So this problem has two parts. The first part asks for the dose, and the second part asks for the number of capsules to be dispensed for one dose. You can solve both parts of this problem using either the ratios and proportions or dimensional analysis. So let's use the ratios and proportions. Determine the dose. So X milligrams is what we want over 60 kg for what the doctor ordered, right? Is equal to 15 milligrams per kg. And that's what we have. So X times 1 is X, 60 times 15 is 900. So then the dose is 900 milligrams. Now let's determine the amount of capsules we need. So X capsules over 900 milligrams is equal to 1 capsule over 300 milligrams. So our numerators units match and our denominator units match. So cross multiply X times 300X is equal to 900 times 1, 900. 900 divided by 300 gives us 3 capsules. Now, if we want to use dimensional analysis, so remember we have to cancel our units. So 60 kilogram over 1 times 15 milligrams over kg. That way our units cancel. So 60 times 15 is 900 milligrams. So determine the number of capsules. So what we got on the first problem. So 900 milligrams over 1 times 1 capsule over 300 milligrams. Okay, so 900 divided by 300 goes 3 capsules per dose. One-step method. So if we just wanted to know the number of capsules, we can do this problem in one step. We just have to make sure to cancel our units. Okay, so 60 kg over 1 times 15 milligrams over kg. That'll cancel our kgs. And then the next step is 1 capsules over 300 milligrams. That way our milligrams cancel and we're left with capsules. So 60 times 15 times 1 divided by 1 divided by 300 is equal to 3 capsules. Okay, and this one-step method would only be used if they were only asking for the number of capsules. But since they're asking for the dose and then they're asking for how many capsules, that's why we have to do 2 steps. Calculating dose based on body surface area. So body surface area is the measurement that is based on the patient's weight and height, variable and expressed as meters squared, m over 2. m to the second. So BSA can be estimated using a nomogram, a graph used to show the relationship between two or more values. Table 4.6 outlines the steps for using a BSA nomogram, and figure 4.2 and 4.3 are nomograms used for estimated BSA for children and adults. So some medications, such as chemotherapy medications, require a BSA to calculate a patient's specific dose. So remember that whenever a patient is going through chemotherapy, their weight fluctuates a lot. So every time that they're going to go get a chemotherapy, they have to weigh the patient and calculate their BSA. If their BSA changes, then the medication dosage has to change. So this is something that will be always calculated per day, per week, depending on how often the patient comes in. Sometimes patient comes in twice a week, sometimes once a week, sometimes biweekly, depending on how aggressive they want to be with the chemo. Okay? So here's an example of a nomograph for children. So we have the height calculated in centimeters and inches. So remember, if they give us the result in feet, we have to calculate that into, or convert it into inches. Okay. The middle part is the body surface area. So this is the meter squared that we're looking for in order to calculate our dose. And then the third column is the weight. And again, it's written in kilograms and pounds. And this is the nomograph for adults. And again, so height is in centimeters and inches. Body surface is in the middle. And the weight is in kilograms and pounds. So our steps. So first, mark the patient's height on the left column. Then mark the patient's weight on the right column. You draw a line or place a straight edge on two marks. Determine the BSA by noting where the straight edge crosses the center column. When the straight edge crosses between two numbers, the BSA should be estimated to the nearest 1/2 unit. So those are our steps. Another way to calculate the BSA is also using an equation. A popular equation to calculate the BSA is the Mosteller method. This formula takes the patient's height and weight into account. The Mosteller method formula is shown below. So BSA in meters squared is equal to the square root of the height in centimeters, so pay attention to that, it's in centimeters, times the weight in kilograms, divided by 3,600. Okay, so again, the equation will probably be more accurate, while the monogram, it's an estimate, and especially when it lands between two numbers and you have to estimate that or round off. So it might be a little bit different, okay? So let's give an example. So a patient is 180 centimeters tall and weighs 110 kilograms. What is the patient's BSA? So let's use the formula. So 180 centimeters times 110 kilograms divided by 3,600, and you take the square root of that, will give you a 2.35 meters squared. So that's the patient's BSA. The BSA could also be estimated using the monogram in 4.3. Calculating pediatric doses. So if a manufacturer does not suggest an exact pediatric dose for a medication, such as a dose based on body weight or BSA, an appropriate dose may be calculated using the normal adult dose and one of several formulas. So there are two different formulas that we can use to calculate the pediatric dose. And again, this is pediatric dose. This is not an infant dose. So pay attention. The Young's rules bases the suggestion dose on the child's age in years, while the Clark dose bases the suggested dose on the child's weight. So both formulas indicate the usual adult dose, but because the manufacturer often provides this as a range, such as 20 to 30 milligrams, the physician or the pharmacist must determine the usual dose for the purpose of the formula. So Young's rule. Age in years, again, divided by the age plus 12 years times the adult dose will equal the pediatric dose. Clark's rule, which is in weight, so it'll be weight in pounds divided by 150 pounds times the adult dose is equal to the pediatric dose. So let's do an example. A 6-year-old child needs a dose of medication that has a suggested adult dose of 500 milligrams. Using Young's rule, what is the appropriate pediatric dose? Round to the nearest milligram. So we're using Young's rule. That means we're using the years of the patient. So 6 years divided by 6 years plus 12 times 500 milligrams is equal to 166.66 milligrams. And we're always going to round down for pediatric doses. Okay, so it'll leave it as 166. Now using Clark's rule. An 80-pound child needs a dose of medication that has a suggested adult dose of 250 milligrams. So round to the nearest milligram. So 80 milligrams divided by 150 times the dose, 250 milligrams, is equal to 133.33 milligrams. Again, we're always round down. So the answer stays as 133 milligrams. So chapter summary. The basic unit measure in the metric systems are meters, length, gram, weight, liter, and volume. The metric system uses prefixes that describe the value of units by multiples of 10, 100, or 1,000. The milligram and microgram are the two most common units of weight measured in pharmacy. A gram weighs about the same as a large clip of paper. The liter and milliliter are the two most common units of volumetric measure in pharmacy. The meter and the centimeter are the two most common units of measure used to describe length and height in healthcare settings. A meter is about the same length as a yard or 3 feet. Converting units into the metric system often requires multiplying or dividing by 1,000, or moving the decimal point 3 places when changing the unit of measure. Use a ratio proportion method to convert the units. If you need a foolproof way to perform the conversions, especially if you're getting confused as to which direction you should move the decimal point. The dimensional analysis method can be used using converting units of measure. When solving a story problem, remember to identify what the question is asking. Then designate this unknown value with the letter X when writing your calculations. Always double check the units in the numerator match on the both sides of your ratios and proportions, and the units of the denominator match as well. When solving for x, cross out cancel units to verify that you are left with the correct unit. You should always check your answers by multiplying the means and the two extremes in your ratios. The two products should be equal. Pediatric patients often need a dose customized for them based on their weight. Body surface area is used to calculate some patients' doses, especially chemotherapy agents for pediatric patients. Clark's rule and Young's rule are older methods of calculating the pediatric dose on what is normal for an adult dose. And that ends our PowerPoint. So let's go over some problems on page 121. Let me see. No, not the way. So let's see. It says determine the BSA for each patient described using the Moseller method. Then use the BSA nomogram to determine the following BSA values. So it says a child of normal weight and height is 28 inches and 20 pounds. So if we look here at our monograph, I think I brought the wrong one. Hold on, let me get the correct monograph. Okay, so let's see, this one I believe is a child monograph. So let's go back to problem. So the patient weighs 28 inches. I'm sorry, the height is 28 inches. The patient weighs 20 pounds. So if we use our monogram, so we're gonna put our dot here at 28, correct? And at 20 pounds, it should be here. Oops, here somewhere. 28. Okay, and now we're gonna use our straight edge. Well, that's not straight. It's harder than I thought. But if I use my straight edge, it goes around 0.40 meters squared. Okay. And if we use the equation, let's see. Where's the equation? Okay, here it is. So if we use the equation, it says to use, I'm just gonna write on here, the square root centimeters times kilogram divided by 3,600. So it's giving us the information in inches. and it's giving us the information in pounds. So we need to convert first. So let's see. 1 inch is equal to 2.54 centimeters. And then we also know that 1 kilogram is equal to 2.2 pounds. Well, let me just change it to the whiteboard instead. Okay, let me write this down again. So 1 inch is equal to 2.54 centimeters. And our child is 28 centimeters. So let's set up our ratios and proportion. So 1 inch over 2.54 centimeters is equal to x inches over 28 centimeters. So we're gonna cross multiply. So 28 divided by 2.54 gives us 11.02 inches. Oh, sorry. This is wrong. I'm like, that doesn't sound right. It's the patient doesn't weigh, I mean, the height isn't 28 centimeters, it's 28 inches. That's why we want 2 centimeters. Ay, ay, ay. It's been a long day. Sorry. So 1 inch over 2.54 centimeters is equal to 28 inches over x centimeters, because that's what we're looking for. So now 28 times 2.54 is equal to 71.12 centimeters. And now convert our pounds to kilograms. So we know that 1 kilogram is equal to 2.2 pounds. And we have the patient weigh 20 pounds. So let's set up our ratios and proportions. So 1 kilogram, 2.2 pounds is equal to x kilograms over 20 pounds. So cross multiply. X is equal to 20 divided by 2.2. And that will give me 9.09. So it says to round to the nearest hundredth. So that's the hundredth and that's the hundredth, so we're okay. So now let's use our formula. BSA is equal to the square root of 71.12 centimeters times 9.09 pounds divided by 3,600. Okay. Oops. Sorry, this is not pounds. This is kilograms. Telling you. So if we set up that in the calculator, so 71.12 times 9.09 is equal to divided by 3,600 is equal to 17.9578. And we're taking the square root of that. So x is equal to 4.237. So if we round off, 4.24. Okay. And when we actually measured less than that. Let me see. 28 and 20. We got 0.40. I must have done something wrong. Okay, so this is where I messed up. So when I divided this was actually 0.179 and change. And so I'm going to take the square root of that and I get 0.42. And when we measured in our monograph, we got 0.4. So this is normal. And this is the actual BSA from the formula. So they might fluctuate a little bit because again, we're using the monograph and it's not as accurate. I keep saying nomograph. Okay. So like we basically see that the formula is more accurate than the nomogram. Let's do another one. See if I could get this one right. Clear. Okay. So let's go ahead and do number 3. So a child of normal height and weight are 48 inches and 48 inches and 51 pounds. So again, we know that 1 inch is equal to 2.54 centimeters and 1 kilogram is equal to 2.2 pounds. Okay, so let's set up our ratios and proportion. So 1 inch over 2.54 centimeters is equal to 48 inches over x centimeters. Cross multiply. So 48 times 2. Turn my calculator. Okay, 48 times 2.54 is equal to 121.92 centimeters. So now 1 kilogram over 2.2 pounds is equal to x kilograms over 51 pounds. So cross multiply, 2.2x equals 251 divided by 2.2. So 51 divided by 2.2 equals 23.18 kilograms. Okay, now we can set up our formula. So BSA is equal to the square root of 121.92 centimeters times 23.18 kilograms divided by 3,600. Okay, so let's put that in the calculator. Times 23.18 divided by 3,600. And we take the square root of that. We get 0.886, and we're rounding to the hundreds. So that is equal to 0.89 meters squared. And let me just double check. We're doing problem number 3. Yep, 0.89 meters squared. So we're good here. Let's go on over to and do problem number 25. So number 25 states, a pediatric patient weighs 23 pounds and 32 inches in height. The manufacturer, Acyclovir, has a recommended dose of 250 milligrams per meter squared every 8 hours. The physician has ordered 200 milligrams of Acyclovir TID. Is the physician order safe according to the recommended doses? Okay, so let's write down what we know. 23 pounds, and he's 32 inches. The recommended is 25. 250 milligrams per meter squared every 8 hours. And the physician has ordered 200 milligrams TID. Okay. So first of all, we want to know the dose of the patient. So we need to find out the patient's BSA in meters squared. Okay, so again, using the nomograph or the dose, calculating the dosing, we have to convert first the inches and the pounds. So 1 inch is equal to 2.54 centimeters over, and it equals 32 inches over X centimeters. Cross multiply. So 32 times 2.54 is equal to 81.28 centimeters. Now 1 kilogram is equal to 2.2 pounds is equal to X kilograms over 23 pounds. So cross multiply. 23 divided by 2.2 gives us 10.45 kilograms. So let's use our formula. So BSA will equal the square root 81.28 times 10.45 divided by 3,600. So 81.28 times 10.45, divide that by 3600 and take the square root of that, gives us 0.485. So we're going to go ahead and put 0.48. So let's rewrite this. So our BSA is equal to 0.48 meters squared. Now the physician ordered the recommended dose is 250 milligrams per meter squared. So 0.48 meters squared goes on the bottom. X milligrams is what we're trying to find. Cross multiply to 250 times 0.48 gives us 120 milligrams every 8 hours. So the doctor ordered 200 milligrams. That is greater than 120 milligram dose. So is the physician order safe according to the dosage recommended? No. The answer would be no. So these are the problems that you guys will be doing for homework. I hope this helps. And again, if you have any questions, please feel free to message me and I'll reply to you as soon as possible. Thank you. Bye-bye.